Next topic is the central limit theorem. Basically what the central limit theorem is going to allow us to do is, as long as we have a sample that's larger than a magic number size, 30, or we have a sample from a normal population, that sample is then going to take on a normal distribution. So when I talk about this magic number 30, I've taught out of books that have it as 30, I've taught out of books that have it as 40, as 50. Really, it's a number that isn't set in stone, let's say. What's happening is, if I have initially a distribution that's not normal, maybe let's say we have a distribution like rolling a die where you can get 1, 2, 3, 4, 5, or 6. Every bar would be the same, and the distribution would start out like this with 6 even bars. If we then said, what's the average you get from 2 dice? Well, the average that you get from 2 dice would start to look like this. You'd be most likely to get an average of 3.5, and then you'd be least likely to roll 2 1s or roll 2 6s. If now I go to 3 times, 4 times, 5 times, 6 times, on down, what's going to happen is what started as a uniform distribution is going to start to look more and more normal until at some point it exactly approximates the normal distribution. So the idea that it happens right at 30, technically 29 is very close to a normal distribution, 30 slightly closer. What we need to do is we need to pick some number that says, here's where we're going to say, yes, this is close enough that we can use our table. So for your book, that magic number is 30. As long as you have a sample size of 30 or greater, you can say, yes, the central limit theorem applies. With this first type of problem that we're looking at, we're going to be asked, does the central limit theorem apply for this sample? Then we're asked to find the mean, then we're asked to find the standard error. So the first thing I'm going to look at for each of these questions is the sample size n. Since it says it's from a non-normal population, we need that n to be 30 or larger to say, yes, the central limit theorem applies. For number 1, the n is 16, so no, it does not apply. For number 2, the n is 400, so yes, it does apply. For number 3, the n is 20, so no, it does not apply. For number 4, the n is 12, so no, it does not apply. For number 5, the n is 60, so yes, it does apply. And then for number 6, the n is 30. This is just a reminder that it's 30 or more, so yes, 30 does count. Yes, I can apply the central limit theorem at 30. From there, what I can do is find the mean and standard deviation. The mean is incredibly easy. Basically, if I know that I'm picking from a distribution that has an average height of 5'10", then my guess for what the mean of that distribution is 5'10". So even though I could pick out somebody who's 5'3", then 5'4", then 5'7", I could get 30 samples that are all on the shorter end where the average is not 5'10", my expectation is that on average people will be 5'10" if that's the mean of the distribution. This is all to say basically for part B, where I'm asking the mean of the sampling distribution, basically the mean of the sampling distribution x bar just equals whatever the original mean was. So if they gave me the mean was 20 here, the mean of the sampling distribution is 20. Here, the mean of the sampling distribution is 1500. Here, the mean of the sampling distribution is 0.88. Here, the mean of the sampling distribution is negative 800. Here, the mean of the sampling distribution is 75. And here, the mean of the sampling distribution is negative 0.02. So I'm literally just copying the exact same mean as it was and saying that's the mean of my sampling distribution. For part C, where I'm trying to find the standard error, it's a little trickier. The standard error, sigma sub x bar, or the standard error of the sampling distribution, equals the original sigma, whatever the standard deviation was of the distribution that I'm given, divided by the root of n. So even though we know the central limit theorem doesn't apply to numbers 1, 3, and 4, I'm still going to calculate this as though it does. Do notice that the formula calls us to use sigma, but what we've been given is sigma squared. So really we're going to have to take the root of sigma squared first, then put it into the formula. So this is going to become sigma sub x bar equals the root of 4, or in other words, the root of sigma squared to get back to sigma, over the root of n, in this case the root of 16. So when I put this into my calculator, the root of 4 over 16 is really going to give me 2/4 or 0.5. For part C, I'm going to need to take the root of 4,000 over the root of 400. When I put that in my calculator, the root of 4,000 over 400 gives me 3.16. For number 3, sigma sub x bar is going to equal the root of 0.64 over the root of 20. I get that to be 0.18. For number 4, sigma sub x bar equals the root of 2500 over the root of 12. I get that to be 14.43. Just a note, I'm only going to 2 decimal places because that's what I'm used to. Always go to whatever it tells you to round to on Cengage. Part 5, sigma sub x bar equals the root of 100 over the root of 60. I get that to be 1.29. Finally, for number 6, sigma sub x bar equals the root of 0.01 over the root of 30. I get that to be 0.018. Notice that when I do that 0.018, I don't round it to 0.02. I really would prefer to have at least 2 significant digits. So before I was going to 2 numbers after the decimal place, but here, since 0 is the first number after the decimal place, I want to go 1 more.